Alright, let's take a look at chemical formulas. Alright, each molecule has a chemical formula. A chemical formula indicates a couple different things. First thing it indicates is which atoms are found in the molecule, and we typically use the chemical symbol for that. And it tells in what proportion they are found, or how many of those different atoms are found. And that is the subscript, the number, the numeral, and the subscript immediately following the element. Okay, so we have a couple of different examples up here. Hydrogen, we have H, so we know this hydrogen contains 2 molecules of H. Water, we have H2O, we know that we have 2 hydrogen molecules and 1 oxygen molecule. So a chemical formula tells us a lot about a molecule. Now, a molecular compound, okay? A molecular compound is a compound that shares its electrons. Okay? And typically it is made up of non-metals. Starts with a non-metal, ends with a non-metal. Okay, so they share electrons, and typically their difference in electronegativity is greater than about 1.5 in terms of electronegativity. We also have several diatomic molecules that you need to memorize. Alright, diatomic molecules from chemistry 2. These molecules cannot be by themselves in the wild. They're either going to be bound to something else in a compound or bound to themselves. We have 7 diatomic molecules: nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and don't forget about hydrogen. Best way to remember this: it starts at atomic number 7. Remember, nitrogen has atomic number 7. It makes a 7. There are 7 of them, and don't forget about hydrogen. Alright, 7 diatomic molecules. Starts at 7, makes a 7, and don't forget about hydrogen. Remember, they can never be found by themselves. We have 2 different types of formulas. Empirical formulas, which gives the lowest whole number ratio of atoms in each element in a compound, and typically we use these with ionic compounds. And we have molecular formulas, give us the exact number of atoms in each element in a compound. Okay, and that's useful for a couple of different things. A couple examples of molecular formulas would include water, H2O, carbon dioxide, carbon monoxide, CH4, methane, hydrogen peroxide, H2O2. Empirical formulas, these formulas give the relative numbers of types of each element in that compound. Some more types of formulas, rather than just the symbols and the subscripts, we actually can represent their shape or their atom arrangement with a few different types of formulas. Structural formulas show the order in which atoms are bonded. Okay. Perspective drawings show us a three-dimensional arrangement of these different compounds, and this is when we get into molecular geometry a little bit later on in Vesper theory, valence shell electron pair repulsion theory. On this perspective drawing, in order to read it, the hydrogen, anything that's a solid line, is in the plane of whatever it's drawn on, be it the board or the paper. Anything that's dashed is going away from you, behind the board. Anything that's a wedge is coming towards you. Ball and stick models we will actually work with a little bit in class. We use sticks to represent bonds. The balls represent the individual atoms. And a space-filling model takes into account the different hybridization and electron cloud of the different elements. Alright, ions. When atoms lose or gain electrons, they become ions. So in molecules, they share electrons. Ions, they lose or gain electrons. Cations are positive and formed by elements when they lose an electron, so we're taking away part of that negative charge. They then become positive. They are found on the left side of the periodic table. Okay, metals. And the anions are negative charged, and they are formed when they receive electrons, and they are found above the stair step. They're typically the nonmetals. Okay? Now we know in bonding, if we're not sharing electrons, we're losing or gaining, opposite charges must be attracted to one another in order for bonding to occur. Ionic bonds. Ionic compounds, such as sodium chloride, are generally formed between metals and nonmetals. And in an ionic bond, the metal will lose an electron, become positive, referred to as a cation, and the anion, or the nonmetal, will typically receive that electron and become negative or become an anion. And we end up with this attraction between the two. All right, when you lose an electron, your ion becomes smaller. When you gain an electron, your ion becomes larger. Okay, and we also, once you have these charged particles and they come together, they typically form these crystal lattice structures. And we're going to talk a little bit more about those when we talk about inorganic chemistry. Now, let's talk about writing formulas, or bringing this all together. Because compounds are electrically neutral, one can determine the formula of a compound the following way. The charge of the cation becomes the subscript of the anion. So if we're writing the formulas, we write their symbol and we write their charge, and there are some rules for getting the charge, which you should have memorized from Chemistry 1. If not, I will give you a copy of those in class. And then, once you write the symbol and the charge, we will then crisscross those charges to get electrically neutral atoms. The charge on the anion becomes a subscript of the cation. Charge of the cation becomes a subscript of the anion. If these subscripts are not the lowest whole number ratio, meaning if we can reduce the subscripts, we divide them by the greatest common factor. Greatest common factor. And I have some common cations for you. +1. Cations typically are found in group 1, +2, group 2. Don't forget about silver is always going to be +1. Zinc is always going to be +2. We have that little stair step coming down from chemistry. Aluminum is always +3. Cadmium is one we're going to add this year. It's always going to have the same charge as +2. Ammonium is a polyatomic ion that you need to memorize. It's our polyatomic cation, along with mercury 1. It's another polyatomic cation. We have several different elements down here. These are our transition metals. These are typically the charges they are found with, and we're going to talk about how to determine their charges in class. I have a chart to help us determine the oxidation states of those, or the charges of those. I have a few common anions. I have monatomic ions on the left-hand side, polyatomic anions on the right-hand side. You should remember hydrogen can be plus or minus 1. Fluoride, these are group 17. The oxygen group 16. And nitrogen can be a -3. Some of the different common polyatomic anions: acetate, couple different ways to write it, chlorate, perchlorate, nitrate, permanganate, carbonate, chromate, dichromate, sulfate, phosphate, and we have several different more oxy anions that we could talk about.